ask questions. So last time on Monday, we actually have, let's see where we stop. We have introduced the calculations about all different type of the inflow rates for the drainage design. And actually, we did not have enough time to go through the last example to finish the questions. In the last example, we have utilized all the information we calculated in the previous example about the infiltration rate, the groundwater seepage, and also the meltwater rate, inflow rate. And the problem wants us to find out the design inflow to the drainage layer, and which would be the QD as we calculated in the last lecture. They also want to see the QL. That will be the longitudinal drain, which will be the flow drain during each at the unit distance. So for the longitudinal drain, if you have already get the all the information about the designing flow and the groundwater seepage, then it will be very straightforward. Generally for QL, for the first case without any first action, QL would be QD times the width of the road, the entire road, including the shoulder, plus Q1. That will be the groundwater inflow above the drainage layer. So in this case, you will get the result as 0.517 times the width. The width is of the entire road would be the 10 feet shoulder plus 24 feet pavement and another 10 feet shoulder on the other side. That is 44 feet. So with that, you get the final answer as 23.0 cubic feet per day per feet. So this is actually different. If you go to check the unit, it's a little bit different. That's for the last part. This will represent the rate, the inflow rate per unit distance, and this will represent the inflow rate per unit area. And this is these two will represent the result for the pavement without any first action. We also can find out the longitudinal drain with the first action. The equation is the same, so we have QD times L plus Q1. We just skip the calculation. With that, you can find out the longitudinal drain as 39.2 cubic feet per day per feet. So with that, we have the calculation of all the inflows for the pavement design. And the next thing comes to us is how we can remove the waters from the pavement structure. We need to think about the how to design the drainage layers, how to place the pipes under the pavement structure. So with that, as we have already calculated the inflow, which would be the source of the waters in the pavement structure, we will then need to think about designing a drainage system with a capacity which are able to drain all the waters from the pavement structure or drain as much as possible. So the capacity of the drainage system will be the capacity of both drainage layer and the collector pipes. We want to make sure that the by introducing the drainage system, the outflow rate will be higher than the inflow rate. In that sense, there isn't any or the water in the pavement structure or under the pavement layers will not get more over the time. Instead, we will try to remove as much as possible. For the drainage layer, especially for the capacity of the drainage layer, we need to consider two types. The first one is called the steady state capacity. Usually this one will be larger than the inflow rate of the pavement system. And the steady state capacity represents the capacity of the drainage system under the normal situations and how much it can remove the what's the maximum amount of the water can be removed during the unit time and unit length. And the next one is called the steady state capacity. This one will represent the special case, like especially when there's a heavy precipitations and there will be a lot of inflows to the pavement structure. We want to see how the drainage layers can drain the water, or how long the drainage layer can remove all the waters, or at least remove certain percentage of the waters from the pavement structure. And there will be more introductions about the steady state and unsteady state capacities in the next few slides. For the steady state capacity, you can actually just recall this equation to find out the maximum discharging rate for the drainage layer, and which is Q. It's a function of the K, that is the permeability of the drainage layer, S, that is the slope of the drainage layer, and H, capital H, is the thickness of the drainage layer, and L is the length of the drainage layer. So once you are provided with these four variables, you can then calculate the capacity, steady state capacity of one drainage layer. Regarding to the unsteady state capacity, this will be identified based on the ratio between the volume of the water drained since the rain stops. So if there's a heavy rain, we will try the number of the volume of the water will be maximized at the end of the when the rain just stopped. And then we're gonna check the ratio between the volume of the water and the total storage capacity of the drainage layer. And this one can usually be represented by how the time when what kind of percentage of the water can be drained. This equation shows the time of 50% drainage, and the value, the time is also a function of K, H, S, and L. In addition, it's also a function about the effective porosity of the drainage layer. So there will be 5 parameters to determine the time for 50% drainage. And in addition, for the general case, the degree of the drainage also depends on the time factor and the slope factor. So the time factor is for both factors, they will be identified by these two equations. They will be determined by the permeability, the thickness of the drainage layer, the time to drain the certain percentage of the water, the effective porosity, and the length of the drainage layer, and also the slope. So this figure actually shows the degree of the drainage layer, where the vertical axis represents the degree of the drainage, and the horizontal axis represents the time factor, which would be capital TF. Each line will represent the slope factor. So here you can see that if the time factor is smaller, it usually means that the degree of the drainage is smaller. We're going to use this value to represent the drainage system has the better performance. And also, if we have the larger slope, which means that which will usually have the larger slope factor, and of course the drainage, the degree of the drainage will also be smaller, and with that you have the better performance of the drainage. So this is the previous figure shows the general case, and in this figure we can actually show the relationship between the time and the slope factor for 95% drainage. This relationship is quite intuitive. Usually with a higher slope factor, which means that the slope of the road, the pavement is higher, then the time factor would be smaller. And this indicates that the time for the drainage system, the drainage layer to remove the water will be shorter. So this is intuitively correct. Usually with the higher slope, you can remove the water faster. And based on the AASHTO drainage recommendation for the time to drain from 100% water to 50% water, based on this time, we can identify the quality of the drainage layer. If the time to remove 50% of the water is less than 2 hours, we say that the drainage layer is excellent. If it's 1 day, it's still a good drainage system. If it's less than 7 days, is acceptable. But if it's over 1 month or does not do anything, then we claim that they are not appropriate for the drainage system, and we probably need to reconsider changing the grain size distributions or adding the pipes to improve the capacity of the drainage layer. So that's for the drainage layer. And now let's see one example to see how we can find out the capacity of the drainage layer. Assuming that we have a drainage layer with a slope of 0.02, the thickness of 0.5 feet, and the length of 22 feet, and we also know the permeability K as 6,000 feet per day, and the porosity N is 20%. We want to find out the steady state capacity and the time for 50% and 95% drainage. So first of all, for the steady state capacity, that one is pretty simple. So we can just call the equation Q equal to K times H times S plus H divided by 2L. We know that K is 6,000, H is 0.5, S is 0.02, H is 0.5, and L is 22. So with that, we can find out the steady state capacity. It's 94.1 cubic feet per day per feet. And so that's the steady state capacity. The next one is the time for 50% and 90% drainage. For 50% is also very straightforward. We have the formula to calculate T50. So T50 is NE times L square divided by 2K times H plus S times L. So NE is 20%, L is 22, 2 times 6,000 times 22 plus S is 0.02 times L is 22. So with that, we can find out the time for 50% drainage is 0.21 hour. So what do you think the quality of this drainage system? If the time is less than with times 0.21 hour.
And then excellent.
Yes. Well, as long as the value is less than 2 hours, we will claim that it's excellent. And also this is our design target. We want to make sure that the drainage layer can reach to the excellent quality. And the next one, we want to find out the value of T95, which is the time to drain 95% of the water. So, so with that, we will need to actually call the figure in this page. This page is actually showing the relationship between the time factor and the slope factor. The time factor, in the time factor, you can find out the time for 95% drainage. So we need to identify SF. With SF, we can then estimate the TF and then calculate the T95. So to do that, we first calculate the slope factor. The slope factor is actually a function of the length of the pavement, the slope, and the thickness. So the length is 22 times the slope, 0.02, and the thickness is 0.5. So we get the slope factor is 0.88. If we go to check the value of 0.88 in the graph, so this would be the more accurate graph. 0.88 would be some value around here. And if we go to check the result, you will find out the one point in the y-axis, which is about 1.8 for the TF. So what do we get from the graph? We have TF equal to 1.8. And we know that the TF equals T95 times K times H divided by NE times L squared. Here we know the value of K, H, NE, and L. And with that, we can easily find out the value of T95 as 0.058 day. You need to be very careful about the unit of the time. And that will be 1.39 hour. So this is a drainage layer with very good quality. Okay, and so that's for the drainage layer. The other part of the drainage system is the collector pipes, and this one will try to collect the water from the drainage layer and discharge the water from the pavement structure to the trenches that we designed at the edges of the pavement. And usually we will design the longitudinal collectors with some transverse collectors only at those critical points. With that, we can collect as much water as possible and also save the budget so that we can realize find out the balance between the budget and also the drainage requirement. And or as we described previously, we can use different type of the pipes, such as the perforated pipes, the slotted pipes, or the open joint pipes to remove the water. And each one will have their own features, and we have already discussed their permeability requirement and filtering requirement in the previous lectures. But in the designing procedure, we need to actually in the design of the drainage layer, we need to consider the types of the pipes that are going to use for the drainage system, the location and depths of the transverse and the longitudinal collector pipes and the outlays. We also need to find out the slope and the size of the pipes, and also the provisions of the adequate filters to protect the pipes should also be included, so that the pipes can last for a longer time without any maintenance. So we will go through the design consideration one by one. So first, for the slope of the pipes. Actually, the slope of the pipes is determined by the longitudinal roadway grades and also the cross slopes. In general, we will have some empirical standards. Usually for the smooth bore pipes, the slope will just need to be a little bit larger than 1%. But for the corrugated pipes, we have to set a larger slope and make it, or at least make it higher than 2%. So that's the slope setting for the pipes. And regarding to the locations and the depths, this is actually related for the locations and depths of the pipes that you want to install for the pavement structure. This one is actually related to the amount of the groundwaters or the and also the frost action. If there isn't any groundwater or the frost action, then we can just place the pipes in some narrow trenches. It could be just next to the edges of the pavement, or it could be placed at the edges of the shoulder. Either way is fine. And this is for the pavement without any groundwater or the frost action. But if there's any groundwater or if there's any consideration about the frost action, we need to put the collector pipes at very deep trenches, so that we can prevent the impact of the frost action. And also we are able to use these pipes to collect the groundwater seepages. And for the collector pipes, we also need to have some, we have to design them based on the consideration of the permeability for the drainage layers. Usually the drainage layers applied for this trenches should satisfy this condition, at least to make sure that the permeability should be higher than the discharge per unit length of the trench divided by the width of the trench. So this is the requirement, the permeability requirement for the materials applied for these trenches. Also, similar to the previous condition, the collector pipes can be placed either at the edges of the pavement or at the edges of the shoulder. Either way is fine. So that's the where we're going to place the pipes. And the next thing we need to consider is the discharge capacity of the collector pipes. We want to see how much water can be discharged by the pipe. So this equation actually shows the capacity of each type of the pipe with respect to a specific size. So here Q is the discharging capacity. The unit is cubic feet per day. And N in this equation is the roughness coefficient. And this one is related to the type of the pipes. Here you can find out the coefficient, the roughness coefficient for each type of the pipes, depending on the materials of the pipes. For the clay drain tire, the roughness coefficient is between 0.014 to 0.018, but for some smooth plastic pipes, their value is the coefficient is between 0.008 to 0.012. And also the capacity is related to the area of the pipe, which would be the area of it's related to the diameter of the pipes, and that's A. And also we have to consider the hydraulic radius of the pipe. And SC would be the slope of the pipe. That would be the feet per feet. It's related to how you're going to place the pipe and how you're going to control the flow rate in the pipe, the directions of the flow in the pipe. The last thing we need to think about in the design is identifying the appropriate size of the pipe based on the inflow and also the capacity of the pipe. So this equation shows the minimum diameter requirement for the pipe. Here in this equation, you have the value of n, that will be the roughness coefficient. You have the QL, that will be the longitudinal drain, as what we calculated from different sources of the inflow. And L0 is the distance between the two outlet points. So it basically shows the length of the pipes from two outlet points. And with that, you can calculate the minimum diameters. And here I'm going to show you one example about how to find out the size of the collector pipes. In this example, we are considering corrugated metal pipes with a roughness coefficient of 0.024, and it's placed at a 2% slope in a stretch drain, and the outlets are provided at every 500 feet, and the lateral flow is 39.2 cubic feet per day per feet. And we want to find out the diameters for the pipes required for the drainage system. So in this example, we are given the value of n as 0.024, slope as 0.04, the lateral inflow rate would be 39.2, and the length is 500 feet. So with that, we can find out the value of diameter, which would be the minimum value of the diameter. So in the solution, we can just recall the equation we have in the previous page. D equal to n times QL times L0 divided by 53 times S to the power of 0.5 and to the power of 0.375. And with that, we have the value 0.024 times 39.2 times 500 divided by 53 times 0.02 to the power of 0.5 and to the power of 375. So with that, you get the minimum diameter for the pipe is 4.72 inches. I'm sorry, I guess so I think I just accidentally removed everything. I will just type everything again. So for the calculation, so D equal to NQL L0 53 as 0.5. So if we apply all the values in this equation, you can find out the diameter is 4.72 inches. And this is approximately 120 millimeters. So with that, you can consider applying something, say that the pipes with a diameter of 5 inches as your design, so that you can satisfy the requirement of draining the lateral flow, the lateral inflow of 39.2 cubic feet per day per feet. Okay, so that's the okay, I guess that's the all the topics about the just a moment. I guess there will be. Okay, sorry, I just accidentally turned off the tab. So that's all topics about the drainage design, and I think I have enough time for you to work on the in-class questions. So I will enable the let me enable the in-class questions on Avenue to Learn, and with that you can start working on the questions, and if we have enough time, I will help you to go through all the answers. So so for now, you are able to go to Avenue to Learn. So just a moment. And in the assessment, you can find out the quizzes. And I will just make it visible. I will try to make it visible. Okay. So with that, you can see the questions. There will be 2 multiple choice questions, and you can work on these 2 questions, and we will have 10 minutes to work on that. So I will go back to review the answers of these 2 questions at 5:15. Okay. Okay, so I think it's time for you to work on the quiz.
Doctor, we can't start the quiz because it says that the quiz period not started yet.
Oh, it does not start. Let me just modify this one a little bit. Try to remove everything. Okay, I guess I have this one. Oh, I just accident. I previously assumed that we're gonna start at 5:10. Okay. So can you see it now?
Yes.
Okay, good. You can work on it. This is about the general questions of the drainage design. You can go, when you work on this one, you can go back to check all the slides of the drainage design. I guess it's from node 9 to node 13, including the lectures today. Try to go through them and work on the questions. As long as if you know the concept, it could be easy for you to work with. Okay, I'm gonna mute myself to not interrupting you. Okay, do you need more time to work on the questions? Or any questions do you have so far? Okay, so I guess I can go through the first all these two questions, and for the as this is the first time for us to introduce the in-class questions, for this time I will not grade based on your based on your right answers, so just based on your attendance. And you can try to check the answer for now and see how you're going to solve these two questions. Next time, I'll just try to leave enough time for you to work on the questions and grade based on whether you get it right or not. So for the first problem, you are provided with the soil with a given percentage of passing for different size of the sieves. For number 20, number 40, and number 60, the size of the number 20 sieve is a 0.85, 40 is a 0.425, and 60 is a 0.25. The percentage passing is a 25% for the number 220 sieve, 18% for 40 sieve, and 13% as for the number 60 sieve. We want to find out the effective size for 20% passing. So to solve this question, you need to recall the formula that we defined previously for the log dx equal to log dA plus x minus a b minus a log db divided by dA. So this is the equation we're going to use. And we have to make sure that a is smaller than x, smaller than b. So this is a condition for us to use this formula. And in this case, x equal to 20. So we need to find out which two values we have to use to calculate the effective size. Apparently, 20 is between 18 and 25, which means that we have to use the number 20 sieve and number 40 sieve. So for this case, we have a equal to 18 with D18, that is 0.425, and B equal to 25, and D25 is 0.85. So we put this information in this equation. So with that, we have log dx, not dx, d20 equal to log dA is 0.425 plus 20 minus x is 20, a is 18, and b is 25, a is 18, and the log dB is 0.85 and dA is 0.425. So you can get the result as minus 0.285, 285.6. So with that, you get a D20 equal to 10 to the power of minus 0.2856. That will give you the result as 0.518 millimeters. So you should use that value because the result is randomized, and I don't know what kind of options you choose, but this is the right answer. For the second question, it's simpler. We know that the height of the groundwater table is 5 meters. So that would be H, capital H, that is 5 meters. And the vertical distance between the bottom of the drainage layer and the impervious layers is that is H0, that is 3.5 meters. And we want to find out the value of the distance influenced by the groundwater, which means that we want to find out the value of Li. And we actually have the formula Li equal to 3.8 times H minus H0. In this case, that would be 3.8 times 5 minus 3.5, which will give you the result as 5.7 meters. So the right answer for the second question is 5.7. Okay, I think that's all for the in-class quizzes. Do you have any questions? Okay, if there's any questions, I think that will be all about the lecture today. And with that, I will close the meeting. Thank you very much for your time. And we will continue the lecture tomorrow by introducing the S4 technology. This point is related to the third lab experiment. And there will be more details introduced in the lecture tomorrow about how the experiment will be, how the demo will be conducted, and also what's the major contents will be included in that topic. Okay, I think that's all. Thank you very much, and I really appreciate the attendance. With that, I will close the meeting today, and I will see you tomorrow.